In today's notes, we're going to start working on proofs dealing with line segments. So we'll do the notes part first, then we'll do some examples. To start off, we have some similar justifications to the ones that we used in algebraic proofs, except these in the world of geometry become properties of congruence instead of properties of equality. So we had a reflexive property of equality that said if something is equal to itself. So reflexive POE was something like AB, the length is equal to AB. Whereas the reflexive property of congruence, so we'll call that POC instead, looks more like segment AB is congruent to segment AB. Pretty much the same meaning, but we can look at the symbol in between. So the fact that there's a congruence symbol here and an equation or equality symbol here tells us whether we're using POE or POC. So these other ones also have counterparts in properties of congruence. So symmetric, I'm not going to rewrite all the POEs. We did those in the algebraic proofs video. So we'll do symmetric POC. So that's if I have something like angle 2 is congruent to angle 3, but in fact I need to say the other way around, then I'm able to say that angle 3 is congruent to angle 2. It just lets me swap the left-hand side and right-hand side the same way the property of equality did. Next one is transitive POC. That's not how I spell transitive. Let's try again. Transitive POC. Transitive POC works just like the property of equality. We have something that is equal and forms a chain of values. So this would be something like segment AB is congruent to segment CD. And then we need a second statement. There's kind of two inputs to this property. Then the other one would be something like segment CD is congruent to segment EF. Then we can chain those together. So since the middle part is the same, and we have CD and CD, we can chain those together and say the conclusion AB is congruent to EF. So basically take out the CDs in the middle and just have AB congruent to EF. Remember, this is like the law of syllogism from deductive reasoning. Same exact idea. We chain statements or ideas together. The last one is substitution. So we said that we could substitute anything that was of equal value with substitution or substitution POE. In the world of congruence, it works exactly the same way. So if the thing is, it's like there's not cases where you would use it. So, but basically, it lets you substitute a thing for a thing. We're much more often using transitive for POC. But substitution says if things are congruent, you can swap them out for each other in statements. All right, new things for segments. So these are definitions, postulates, and theorems. So those were our properties up above. Now we're going to move into definitions. So definition of congruent segments, or simply definition of congruence, says that if two segments are congruent, so if AB is congruent to CD, then if and only if, so we have a biconditional, because definitions should always be biconditional. So AB is congruent to CD if and only if the length AB is equal to the length CD. So that's our way to switch between the world of geometry, where we use congruent, and the world of algebra, where we use equals. So it basically swaps us between universes of geometry math and algebra math. Next, we have definition of midpoint. I should write it out for the initial thing, right? Midpoint. I will often abbreviate that as definition of MP. But definition of midpoint is going to turn the word midpoint into something mathematical. So we would start with something like the statement K is the midpoint of a line segment like JL. So if we wanted to sketch that over here, that would be a line segment with 3 points, J, K, L, and L is the midpoint, meaning the two half segments are congruent. So the conclusion from this is exactly what we saw in the drawing, is that the two half segments are the same length. So definition of midpoint tells us that in this case, JK, the length, will be equal to KL. So note that this gives us an equal to, not a congruent to. So definition of midpoint tells us that that is equal in length, not necessarily congruent, although they are the same according to the definition we just did. Now, this isn't quite a biconditional as written, because I could draw it a different way with J over here, K here, and L here, where these are congruent, but K is not the midpoint of JL. So there's a second kind of hidden part to the conclusion, which is that K is between J and L. Usually we don't write that in a proof. We kind of observe it from a drawing. So remember that betweenness, or the idea that a point is collinear and in between two others, is something we are allowed to assume based on a drawing. So if I have a drawing like this that has points A, B, and C, I can assume that that this whole line, segment AC is straight, that it doesn't like have bends or curves or angles to it. And I can assume that B lies on that segment, that it's coincident with the segment, and that it is between A and C. So we need both of those to make this a biconditional. So if we know that JK equals KL and K is between J and L, that would give us this first picture up here, and that would let us use the reverse or the converse to say that then K is the midpoint. So yeah, just be aware we do need both of those, but typically this one we're going to be assuming from a figure. All right. If we put those two together, then we get something we mentioned in earlier notes, which is the midpoint theorem. So midpoint theorem is just a way to squish those two together, and we'll use even the same letters. So K is the midpoint of JL. We're starting with the exact same information, but this time our conclusion is going to chain definition of midpoint and definition of congruence together to say that segment JK is congruent to segment KL. So if you call it midpoint theorem, then you can have a conclusion that says they're congruent instead of equal. Note that theorems are always one-directional. They're not biconditionals like definitions, so I'm only going to draw this arrow one way in this case. All right, we could make it a biconditional in the same way, but theorems are not intended to be biconditional. They're one-directional properties. All right, our last thing, last thing to talk about here is our one postulate for segments, which is the segment addition postulate. Segment addition postulate says that if, let's pick some new letters, if Y is between X and Z, so that means in a picture, these are collinear because between requires collinearity. So I now have X, Y, Z for my picture. If Y is between X and Z, then we know that X, Y, the left side of that segment, plus Y, Z, the right side of that segment, is equal to the entire segment X, Z. So that's our one postulate within segments, and it lets us add two segments together to make a longer one, but it only works when the one point is between the other two. Again, this is typically assumed from a figure rather than explicitly stated within the proof. It certainly could be, and if we were being very rigorous about our proofs, we would want to, in the proof, claim or say in a statement that y is between x and z, and our reason for that would be that we assume from the figure. We're not going to be that rigorous. We're not going to include that step in our proof, but we certainly could if we wanted to. Okay, that's our notes. So these are all the properties that we're going to use. We also will still use some of our algebraic properties. So notice that with that postulate, we ended up with an algebraic equation, and with definition of midpoint, we had an algebraic equation. That would then allow us to bring in our properties of equality and do some algebraic work with this as well. So that's the note section and the properties we can use. The rest of the video is going to be going through some example problems. So I would recommend, if you haven't had a chance to try these proofs on your own, or maybe watch the first one and then try the others, and then use the video to check your work or to try to help you if you get stuck. Because just watching it, you're not going to internalize it as well as if you try it on your own. So I'm just going to go through these 5 examples one by one, and if there's a particular one that you want help with, you can skip ahead to that one to find how I did it. Also keep in mind with proofs, there's typically more than one way to do them. So just because I did it a certain way, that doesn't mean it's the only way to do it. You just need to make sure that all of your steps are valid and make sense. Okay, so we're going to start this proof, and we should always start proofs by marking up our drawing. So we take the given information, in this case segment KL is congruent to segment LN. I mark that on a drawing by putting these 2 dashes on those segments. Next we know LM is congruent to LN. So that means this lower segment and this right segment are congruent, but I already know that the right segment has this designation for its length. So I know that this one also has that designation. That thought process of linking those together hopefully feels a little bit to you like the transitive property. I said since ln equals this dash and lm equals ln, then this also equals that dash. So it's the exact idea of the law of syllogism, chaining pieces together. And that's what we're going to need in our proof. So now that we have our drawing marked up, I think hopefully we can clearly see that L is the midpoint of segment KM in our drawing at this point. Now we just need to write the proof to show that it's true. So we have our statements on the left and our reasons on the right. And on the left, our first statement is always the given information. We can write each given thing on a separate line or write them on the same line. I'm going to, since this is short, just fit them together. So KL is congruent to LN, and my other statement, LM, is congruent to LN. The reason is that that is our given information. The next thing we're going to do is think about what we marked on the drawing. The first thing that we marked was that this segment and this segment were equal in length. To express that in the proof, I'm going to say that KL is equal to LN, and the thing that let us do that is, I changed the congruence into an equals, so that is the definition of congruent segments. So that gave us KL equals LN, and then we'll also use that same property or same definition to say that LM is equal to LN, because we can turn the other congruent statement in the given into, not L, that is an L, it looks like an angle, L. Okay, LM equals LN, also by definition of congruence. I'm going to use this quote symbol, we call that a ditto mark, to just mean that I repeated the same reason as the previous step. It's also totally fine if you want to write out definition of congruent segments again, but it's quicker to write a quote mark. Okay, so now looking at what we have, I'm going to highlight here. We have LN here and LN here. That means I'm going to be able to chain these together to link KL. Oh, I'm doing highlighter still. Whoops. back to the pen, to link KL to LM. LN is the bridge between them. So it doesn't matter what order they're written in. I mean, technically we could use symmetric property to flip one of them around and write ln equals lm so that they then chain together like visually, but we don't need to do that. It's an extra step that we can skip. So think of it as making like a C shape. So lm goes to ln, and then that ln goes over to kl. So we're going to be able to state that KL is equal to LM. Now that we know KL is equal to LM, there's a hidden information. So here it says, what information are we assuming from the image? And remember that we can assume L is in between K and M. I didn't write a reason here. This was transitive POE. So since we can assume that L is between K and M, and KL is equal to LM, then we can conclude or state that L is the midpoint of KM, and the reason is the definition of midpoint. So we're using it in reverse, and remember in our notes we said that to use definition of midpoint in reverse, there's two required things. The segments are equal, and the shared point is in between the other 2 points. So we are getting that missing piece that doesn't show up in the proof as an assumption from the drawing. All right, so that's example 1. Example 2, we have segment PQ is congruent to segment TQ, segment UQ is congruent to segment QS, segment prove PS is congruent to TU. So again, we're going to start by marking things on the drawing. PQ is congruent to TQ. We'll put 1 dash on those. And then we have UQ, we'll put 2 dashes, is congruent to QS, also gets 2 dashes. It says to prove that PS, the entire segment length of the slanting down line segment, is equal to TU, the entire length of the slanting up line segment. So we can tell that now from the drawing because TU is made up of a 1 plus a 2, and PS is made up of a 1 plus a 2, so they must be the same. So now that we have kind of an outline or an idea of how this is going to be built, we can start writing our proof. Statements, reasons. Okay, so number 1 always is our given information. Segment PQ is congruent to segment TQ, and segment UQ is congruent to segment QS. This is given. The next step was to mark those equal length segments on the drawing, and we are going to do that by saying PQ equals TQ. And I'm just going to, in the same step, also say UQ is equal to QS. Both of those have the same reason, so it's okay to put them on the same line, or you can do what we did in the proof above, which was to write one of them and then write the other one on the next line and use a ditto or restate the reasons. So our reason for this was the definition of congruent segments, or just definition of congruence. Now that we have that, nothing here connects, right? PQ, TQ, UQ, QS. None of those fit together, so we can't do anything else with that. But in our talk through, we said that 1 plus 2 equals the total length. So what we described by that is the segment addition postulate. I'm going to use segment addition to say PQ plus QS, that's the 2 parts of the down slanting segment, is equal to the whole segment length, which is PS, and we use the segment addition postulate in order to justify that. Similarly, we need to get TU, which is part of our prove statement, into the proof, and we do that by the other segment, TQ plus QU, is equal to TU. And that's the same exact reason, segment addition postulate. Notice that those didn't come from here. They don't logically follow from a previous step. They're kind of like brand new information that's appearing in the proof. We went from here to here kind of in a straight line. But then this new information and this new information just kind of popped in out of nowhere. They didn't come from the previous steps. And they didn't really come from nowhere. They came from assuming something from the drawing. We assume that Q is between P and S and that Q is between T and U. That's what allows us to write these two statements. So it's kind of weird because it feels like they magically appear, which is why I emphasize thinking about what are we assuming from the figure, because that's the basis of where these appear from. Okay, now we want our goal. So now we're going to think ahead. We've got some good start to this, but we see our end goal is for PS and TU to be the same. So in our proof, PS is right here and TU is right here. The way that we would be able to say those are the same is if we chain these two together using the transitive property of equality. In order to do that, though, the two left sides would have to be identical. So here's where the earlier steps come in. I have PQ here and PQ here, and PQ is the same as TQ. So I'm able to, using substitution, swap in TQ for PQ. I can trade them out. Similarly, QS I have here is the same as UQ, so I can trade in UQ for QS. If I do that, then the left side of both equations will be the same. Yes, I've written UQ in the opposite order of the QU that's down here, but that doesn't matter because UQ and QU are the same number. The length of a segment doesn't matter which endpoint you name first. So UQ and QU, we don't even need like a symmetric property. Those just are the exact same thing. It's kind of like if I name this line segment from Q to U, and I name it QU, and you name it UQ, it makes absolutely no difference. That is the exact same name for the same segment. Okay, so we're going to go about swapping some things. So first, I'm going to do the blue highlighted swap, and I'm going to bring in TQ and replace PQ with it. So TQ plus QS equals PS. So the rest of that line 3 didn't change. It just stayed the same. And our property there is substitution. Substitution is only going to be the reason if we're taking something plus something, so like x plus y, and we're swapping out one of the two pieces, but not the entire thing. If we're swapping out an entire side, that's where we use transitive property instead. Okay, so this is closer. The TQ here matches now, which is good, but the other part still doesn't. So now we're going to put UQ in. We're subbing it for QS using the green highlights. So that lets us then change what we just wrote into TQ plus UQ. I'll go ahead and write it as QU so that we can see that it's the same. TQ plus QU is equal to PS. So let's try to track our steps there. So we combined this step with this step in order to create that. And then we combined this second step again, the other half of it, with this step to create this. So substitution, kind of like transitive, because transitive is a type of substitution, requires two inputs in order to make its next conclusion. So we used substitution again, and it might help if I number my rows here. 1, 2, 3, 4, 5, and 6. So in step 5, we substituted between row 2 and row 4. No, row 2 and 3. Row 2 and 3, we did substitution of the blues, the blue highlights, to create this row 5. And then for row 6, we combined rows 2 and 5. So we took what we came up with in 5 and used the green highlights from step 2 to substitute QU into there. Okay, so then step 7, we're going to take this other segment addition, so that we came up with in step 4, and the one that we just wrote. So let's look now. We have TQ plus QU equals PS, TQ plus QU equals TU. Since the left sides match exactly, we can now chain them together using the transitive property of equality. So transitive POE. And we're linking together step number 4 and step number 6. And the result is that TU is equal to PS, but I'm going to write it the other way because our prove statement wants us to show that PS is on the left and TU is on the right. So by writing it this way, I can avoid using symmetric property later. And then our final step, because this isn't exactly the prove statement, so straight down from here, we need PS segment is congruent to TU segment. And we change from equal to congruence using the definition of congruent segments. So I want to point out, so that's the complete proof, but I want to point out that at step 2, we use definition of congruence to switch from geometry world into algebra world. And then in step 8, we use definition of congruence again to swap back into geometry world for our final conclusion. This doesn't always happen, but it's a very common thing that you start very early with definition of congruence and then you end with it at the very end. It's kind of like it bookends your proof. It gets you into algebra to do some work, and then it gets you back out into geometry to prove what you were trying to prove. So I know that this part on the left with the little arrows or the little dots may be a little confusing, so I was trying to be clear with over here saying we put step 2 and 3 together, step 2 and 5 together, and then on this transitive we put steps 4 and 6 together. So that's where those things were coming from. Everything else was just following immediately from the step before it, or step 3 and 4, this came from the figure, and this came from the figure. So seeing where the things are coming from and where they're going might be helpful. Okay, that's example 2. Example 3. Example 3, we're going to need to fix because this is a typo. So this says K is the midpoint. It should say M is the midpoint of Ln. So K is the midpoint of JL, M is the midpoint of Ln, JK equals Mn, and we need to prove this. So, as normal, we're going to start by marking up our drawing. Since K is the midpoint of this segment, we know that these two are equal. Since M is the midpoint of this other segment, we know these are equal as well, but they're not the same necessarily, so we put 2 dashes. Our last given information says JK equals MN. Well, if this one and this one are equal, then that means we don't need 2 dashes. We need 1 dash on these. And erasing that is a logical step of chaining those together. So because this equals this and this equals this, this equals this. I know that was a confusing set of arrows, but we're basically chaining together these equalities, and that's going to be using the transitive property in our proof. We want to prove that KL is congruent to LM. Our drawing already shows us that that's the case, so now we just need to write the proof in order to justify it. So we have statements on the left and reasons on the right. So I'll go ahead and keep with numbering. Numbering is a good idea. 1, 2, 3. Step number 1, maybe more than one step. Actually, since we're going to do this trying to follow the breadcrumbs of things like I did in the last proof, I'm going to put each given information on its own row for the next proofs. So number 1. So our first given is K is the midpoint of segment JL. The reason is given. Our second given information, M is the midpoint of Ln, also given. And the third thing is jk is equal to mn, also given. So lots of given information. For number 4, the first thing we marked on the drawing was that jk equals kl. So we'll go ahead and put that as our first thing. jk equals kl because of the definition of midpoint. So definitions most typically get us from vocabulary, like the word midpoint, to something mathematical, like jk equals kl. So definitions are a good tool to turn words into math. So definition of midpoint, and that came from step number 1. So I'm going to just note that came from step 1. Number 5, we marked that LM equals MN. We got that in a similar way, definition of midpoint, but it came from step 2 because that was where we were talking about that side. Number 6, so since LM equals MN and JK equals KL, the thing that we did to link them together was we used statement number 3 because JK here is the same as MN here. So that means these are the same, and if those are the same, that's going to allow me to chain these together. The problem is they're not the same yet. So first, I need to swap one of those out. So we're going to use statements 3 and 4 together, and we're going to chain them because both of them say JK equals something. So we're going to say MN equals KL using the transitive POE. Transitive POE. And the steps that let us do that were 3 and 4. So because JK was the same, we chained MN equal to that all the way around to KL. So we went through JK and said MN is the same as KL. All right, step 7. Now we can use steps 5 and 6 together to basically link the things we need. So we need KL and LM. LM is here and KL is here. And fortunately, because it's what we did in the drawing, MN is the same for both of them. So since that's the same, we can chain these together using the transitive property. So we're going to go from LM to MN, and that gets us over to KL. So that's our law of syllogism connecting those. So instead of writing it LM equals KL though, I'm looking ahead at my prove statement, and it says I want KL on the left. So I'm going to do KL equals LM. And that's using transitive POE. And it did transitive using steps 5 and step 6 together. Now that those are equal, my last step is for them to be congruent. So KL is congruent to LM using the definition of congruent segments, or just definition of congruence. And that just came from step 7. So that's our walkthrough of number 3. I think it's pretty straightforward for that one. There wasn't much we needed to assume from the drawing because we were told these were midpoints. So that gave us the information we needed, that kind of how it was set up. Honestly, if there was no figure at all, other than the fact we'd want to draw it ourselves, we could write this proof exactly the same without even looking at that figure. Okay, so we've got 3 down, 2 to go. Number 4 is really, really similar, but a different picture to this one, number 2. There's 2 segments. Well, let's do the drawing part, and then I'm probably not going to write the actual proof. So XY is congruent to UV, so that gets 1 dash. YZ is congruent to TU, so that gets 2 dashes. And we want to prove that the top entire segment equals the bottom entire segment. So that's actually the exact same problem, just with a slightly different picture compared to number 2, where we said that the long segments were a 1 dash plus a 2 dash. So number 4 and number 2 follow the exact same structure in their proof, so I'm not going to work out every step because it's the same thing. All right, we will go through number 5 to finish up. So YW is congruent to YZ. YW, YZ. This one might be the same too. We'll see. XY is congruent to VY. And we're supposed to prove, again, the entire longer segments are equal, so this one is also the exact same. It's just another different picture to see that it could look different but follow the same path. Realistically, with just segments and just segment properties, there's not that much interesting that we can do. So these proofs kind of end up looking kind of samey. So this one is identical to the steps in number 2 and number 4, so we'll go ahead and just leave it with the first 3 examples, and number 2 will serve for number 4 and 5 as well.